Okay, so now we can practice some of that Millikan apparatus type stuff that we looked at in the last video. So here we have an argon nucleus balanced inside a couple of plates. We know the forces are going to be equal to each other. So first of all, it's an argon nucleus. I know I need to know the mass, the charge. I've done that type of thing before. So we're going to find the mass and the charge of the nucleus. And we've done this before. The mass is 40, so times the AMU, get 18 protons, so 18 times the charge of proton. And just get the basic mass and charge. So if we do that, we should get a mass of 6.68 times 10 to the negative 26 kilograms. And we've got a charge of 2.88 times 10 to the negative 18 coulombs. There's the mass and the charge. Okay, well, if this thing is balanced, again, we've done this type of thing before, I know that my QE has to be equal to my mg to get that balance. So then I can calculate the electric field. So the electric field would just be the mg divided by the q. So I've got the m, I've got the g, and I can just punch it out and I get my electric field. And I already know my electric field is going up because you'd want the negative plate on top to be attracting the positive nucleus. So if we do all that, we should get around 2.28 times 10 to the negative 7 newtons per coulomb. Okay. All right. So now let's change the situation a little bit. Let's increase the electric field to 3.0 times 10 to the negative 7 newtons per coulomb. Now I know it's not balanced anymore. And one of the things that Millikan actually did was he would change the electric field strength, make the charges go up and down, and do different things with them. And now we can piece things together. So we're going to increase the electric field to 3 to the negative 7, so it's not going to be balanced anymore. So then we are going to find out what the acceleration is going to be of the argon nucleus. All right, well, there's a couple forces acting on this thing. Let's start with the simple one. Let's just find our force of gravity. So we've got our Fg is going to be equal to mg, and that has not changed at all. It's still going to be the exact same mass we had before. So if we do that, we will get 6.55 times 10 to the negative 25 newtons, and of course that force is going down. So I've got that force going down, but now I can also find the electrical force going up. Fe is equal to QE. Actually, I used a capital Q, so I'll try and be consistent. Q times E, and I can find the electrical force. Now it's not going to be 6.55 because it's not balanced anymore. It should be a little bit higher than that. So we have the 2.88 to the power of negative 18, and we'll times that by the 3 to the power of negative 7, and we will get a force of 8.64 times 10 to the power of negative 25 newtons, and that force is going up. Okay, well, I've got my two forces. Now I just do the same type thing we've done before. I've got the force going down. I've got the force going up. All I have to do is take those two forces and find the difference, and that'll give me my net force. So if I find the difference between those two forces, I can see that, I'll use a green one, I can see that the electrical force is winning, and this will be my net force. My net force between the two is going to be like 2.09 times 10 to the negative 25 newtons, and it's going up. The electrical force is bigger than the gravitational force. They have the same exponent. So the net force is up just by subtracting the two. And then all we have to do is the same type thing you guys have done lots before. Acceleration is just going to be the net force divided by the mass. So I'll take my net force, which is right here, divide it by the mass, and I will have my acceleration. So I'll take that 2.09, negative 25, divided by that 6.68 to the power of negative 26. And we've got an acceleration of around 3.1 meters per second squared going up. Okay, so we only changed the electric field just a little bit, so it's just barely creeping up and accelerating at 3. And of course, if we made the electric field weaker, then it could accelerate down. Okay, so just basic Millikan experiment, then we just adjust a little bit, and then we can actually control the charge just a little bit as well. Okay, so let's try something else. Okay, so this time we have a balanced nucleus inside two plates with 2.24 to the -7 newtons per coulomb, and the mass of the nucleus is 8.02 to the -26 kilograms, and I want to know what element it is. Now, what some people might try and do is just use the mass for that and just divide by the AMU mass unit to find out the atomic mass number, but because of isotopes, that doesn't necessarily work. You might get it, but you might not, because isotopes, of course, are different versions of the same element that have different masses by just a little bit. So, I mean, you could try doing it that way, but you may get off a little bit and pick the wrong element by being off by a little bit too much of the atomic mass. So, of course, the element, this is always basic grade 9 science. This depends on the number of protons. It's always about the number of protons. The number of protons defines the element. So we need to find out how many protons it has. So to find out how many protons there are, we need to know the charge, which we can do because we have everything that we need. So let's find the charge. So charge, since it's balanced, the force of gravity would just be divided by the electric field because it's balanced, and we can find the charge. So if we do the mg for this thing and we divide it by the 2.24 to the -7, we can find out the actual charge on the nucleus. So we get 3.51 times 10 to the -18 coulombs. So there is the charge of my nucleus. Now, this charge comes from how many protons we have. So if I take that number and I divide it by the E value, or the charge of a proton, I can find out how many protons that was actually created that charge. So divide that by the E value, so divide that by the 1.6 -19, I will get about 21, well, it's 21.95 protons, can't have partial protons, so it must be 22 protons. So 22 protons are required to make up that charge. And there's only one element in the entire universe that only has 22 protons, and that would be titanium. So that must be a titanium nucleus between the plates. So this is how the Millikan apparatus and electric fields are often used to actually identify elements and actually identify what kind of nuclei you're talking about and that type of thing. There's lots of applications for it actually out there, but this is one of the simple ones using a very simple Millikan type of idea, balancing out nuclei, finding how much charge they have, and then figuring how many protons they must have, and then you can actually identify the actual element on the periodic table.